So the heat lost by the aluminum in this situation and the water in this situation must be equal to the heat needed to melt the mercury and to warm the mercury to the equilibrium temperature. So we're going to set those equal to one another. So we're going to have the mass of the aluminum times the specific heat constant of the aluminum times the change in temperature of the aluminum, delta TA, which would be the original temperature minus the equilibrium temperature, plus the mass of the water times the specific heat of the water times the change in temperature in the water. So obviously A here, subscript A is denoting aluminum, subscript W is denoting water. And this is going to be equal to the mass of the hydrogen. Well, since it's M sub Hg, Hg is the unit for hydrogen here. And then we pulled that out front because both of these values are going to be multiplied by this, the latent heat of hydrogen, L sub F, which is what we're trying to find here in this situation, plus the specific heat of hydrogen, Ch sub G, times the change in temperature of hydrogen, delta THG, which is the equilibrium temperature minus the temperature of hydrogen, which was negative 39 degrees Celsius here. So using this, we're going to figure out the latent heat fusion. We solve for that. So L sub F is going to be equal to the mass of the aluminum. Actually, let's go ahead and do this on a new page so we have enough room. So L sub F is equal to the mass of the aluminum times the specific heat of the aluminum times the change in temperature of the aluminum plus the mass of the water times the specific heat of the water times the change in temperature of the water. So that's everything that was on the left side of the equation. And then we're going to divide by the mass of the mercury, H sub G, or mass of mercury, M H sub G. Okay. And then this is subtracted from this is what was on the right side of the equation, except for L sub F, which we have isolated by dividing by the mass of hydrogen, which is the specific heat of the hydrogen, or excuse me, not hydrogen, the mercury, H sub G is mercury. So the specific heat of the mercury times the change in temperature of the mercury. So delta T, H sub G. Plugging all those values into this expression, we find that this is equal to 1.12 times 10 to the fourth joules per kilogram. We can box that in as our solution to the question.